So we are continuing on our topic of triangle congruence. Yesterday, we introduced side, 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 angle, side. We are expanding that today with three more, the third one being rather unique. So that would be angle, side, angle, and angle, angle, side. The third one, which is rather unique, is called hypotenuse leg. That one's at the very end, and I think there's only one example of that on the assignment. So it's because of its uniqueness, it doesn't happen often. But we are going to be also working with proofs a lot more today, so some good practice there as well. So first one on our list here is angle side angle, usually abbreviated with ASA. States that if two angles and the included side of one triangle are congruent to two angles and an included side of another triangle, then we have enough information to definitively say that the triangles must therefore be congruent. Similar to yesterday's, however, kind of down here bolded, it says included means the side is between the two angles. Just like yesterday, side angle side, that angle had to be between the two sides. Just the reverse for today. So in this diagram that they've given us here, just kind of as a, for instance, the information we've been given graphically here states that if, I'll zoom in, actually, let's see, I want to try to get it to where we can see all of it there. If angle A is congruent to angle D, side AB is congruent to side DE, and angle B is congruent to angle E. Because of their arrangement and the relationship with each other, we have enough with the angle, side, and angle to say that then those two triangles must in fact be congruent. So triangle ABC is congruent to triangle DEF. So basically, we're adding to our list now a third instance. If we can prove all three sides are congruent, that was side, side, side. If we could prove two sides and the included angle was congruent, we had side, angle, side. Now, if we can prove two angles and the side between them are congruent, we have enough for angle, side, angle. So with any proof, you're trying to prove as much as you can definitively to get to one of those situations. So we're going to take a look here. First one's kind of easing us into it. First couple are kind of easing us into it. It's given us the statements. We're just going to have to defend them. I'm also going to use the diagram to kind of help aid us as we go through it. But it is given that SQ, segment SQ, bisects angle RQT and angle RST. And you'll notice that that statement is the first statement in our proof, which that's the easy one. That was already given. Now, that statement alone wasn't enough for me to jump right to my diagram and put some stuff in. That's where the next two statements are going to come in. First one is that angle RQS is congruent to angle TQS. So RQS and TQS is claiming that this angle and this angle are congruent. How can we defend that statement? Sorry? Absolutely. So I'm gonna focus on the first one. You said SQ bisects RQT. So this big angle over here, the word bisect means cut perfectly in half, which means those two resulting smaller angles that are created must therefore be congruent. So our reasoning would just be the definition of bisect. And the next one says angle RSQ is congruent to TSQ. So that's saying that this angle here is congruent to this angle here. And the reasoning for that? Same exact reason, because that given statement said it was bisecting two different angles. So we would say that definition of bisect applies here as well. Fourth statement says that QS is congruent to QS. So that's just right here in the middle. Oops, guess I only need one. How can we defend that statement? The reflexive property. So basically, we talked yesterday how things equal themselves. So QS is QS, therefore they must be congruent, but the official term is reflexive property. And then if I look at the diagram, if I look at this top triangle, I have a congruent or an angle, side, angle, congruent to another angle, side, angle. Do I have enough for ASA congruence? Absolutely. So the final statement is what we were trying to prove, that triangle QRS is congruent to QTS, and that is due to angle, side, angle congruence. Moving on to the second one, also kind of set up for us. The statements have been given. We just need to defend them. We have been told two things, it looks like. JK and LM are parallel. So I'm gonna come over here. JK and LM are parallel. But we're also told JL and KM are parallel. Now there's a neat little trick.
Ain't parallel up and down, though, right?
Parallel means they're going exactly the same way. I think you might be thinking of vertical.
Oh, yeah, I'm tripping.
Yeah, parallel just means they have the same slope, meaning they'll never get closer or further apart. There is a visual trick we use though. If we have more than one set of parallel lines, similar to our hash marks, we can actually use a double set for our second one so that we don't accidentally assume that all four sides are parallel to each other. So the single arrows mean those are parallel, the doubles mean those are parallel. So that was our first statement, which was given. Now, new statements that we need to defend. First one is that angle JKL is congruent to angle MLK. So JKL and MLK, they're claiming that this angle is congruent to this angle. How can we defend that? It's not reflexive because in order for it to be reflexive, it'd have to be the same thing. But I'll give you a clue. Parallel, we should be thinking angle pair relationships. This one's a little distracting because we do have extra parallel lines in there. If it helps, try to ignore JL and KM and just imagine this little relationship right here. Imagine KL is the transversal between JK and LM. I'm gonna nudge us towards the right. Almost. They are alternate because they're on opposite sides of that transversal, but they're not outside the parallel lines. They're inside. So it is alternate interior angles. I'm going to abbreviate it today. Alternate interior angles. Third statement is that angle JLK is congruent to MKL. So that's saying that this angle and this angle are congruent, how can we defend that statement? Same thing. All that's changed is it's focused on a different set of parallel lines. But if you think of it in terms of JL and KM, those are also interior and alternate of that transversal. So they are also alternate interior angles. Then the one that probably doesn't shock us too much, say side KL is congruent to side KL. That's thanks to our reflexive property. So if you look at the diagram, because I've kind of labeled it as we went, it looks like we have two sets of congruent angles, and the sign between them is also a congruent set. Is that enough for angle side angle? Sure is, which is the final statement saying that those two triangles must therefore be congruent, and that is due to angle side angle congruence. Last one before we introduce the next type of congruence. You'll notice this one's all on us now. We're gonna have to make the statements and then defend them. But the given information we have so far is that angle BAC is congruent to angle DEC. So BAC and DEC. And that C is the midpoint of AE. So right off the bat, we need to restate what's been given to us because that's going to be part of our argument process. So the first statement, I'm just going to restate the first part of the given information. Angle BAC is congruent to angle DEC. Was given. And then the second thing that was stated was that C is the midpoint of segment AE, which was also given. So the next two, technically we could make the next two statements in either order. So I'm going to leave it to you. What do you guys first? What's the next thing you see? Either visually or based off of one of the given statements. C is the midpoint. Ah, can you defend that though? It would be nice if it was because it would give us extra information. But unfortunately, if you said that, I would say, prove it. And you'd be hard pressed to find a way to prove it, at least easily. Angle B and D are congruent. How's that? I have fun at this point because I'll give you a small clue. Use what we said in statement 2. That means something. C is the midpoint of AE. That's okay. That's all right. I appreciate when people are honest. So it's telling me very specifically that C is the midpoint of AE. AE is running right through here. Can someone tell me what it means to be a midpoint? To be in the middle. And if you're in the middle, what can you tell me about either side? They're congruent. Middle means exactly in the middle, kind of like bisect also does things right in the middle. So if C is in fact the midpoint of AE, can I safely say then that AC and EC are congruent? So that's going to be my third statement. AC is congruent to EC. Now, some of you might be thinking, could I said AC is congruent to CE? Technically, yes, but be careful. We want to try to make sure we're consistent with corresponding parts, and C is the same in both. So I would try to keep C in the second position on both of those. Well, that'll help us at the very, very end. And why was it I was able to make that statement? Definition of midpoint. Now, that was the only segment that it was a midpoint of, so we're done with that piece of information. Now, if I'm looking at this though, again, I'm going to spoil some of the surprise. We're in the section that is angle side angle congruence. So I'm thinking angle side. In order for it to be angle side, we have to be able to defend that these are congruent, because that would only give me angle side angle. So let me ask you this. Are these congruent? They are vertical. So even though that's way, 2 units ago, still comes up. So we can say, and we want to make sure we're careful with our order here. I'm going to say angle ACB which is from my triangle here on the left, is congruent to angle, and here's where I need to be careful, ECD. Notice the pattern I use. I went from A to C. So I'm going to match my diagram. E to C would make sense then, to make sure I'm staying consistent, corresponding parts. And Shanitha, you said that was because of vertical angles? Okay. So then looking at my diagram, I see two pairs of congruent angles, and the side between them is congruent as well. Is that enough to make my proven statement? I think so. I think we can say that triangle ABC is congruent to triangle EDC. And that's all thanks to angle side angle congruence. Now, quick spoiler alert on the assignment for today. It is chunked out based off of what type of congruence you're going to be looking for. So make sure you read, I think it's bolded, read the instructions, because it's going to say prove like numbers 1 and 2 using angle side angle, 3 and 4 using angle side. That'll at least help your eyes think, okay, this is what I'm looking for, and hopefully nudge you in the right direction. All right, so 3 good examples of angle side angle congruence. We're going to transition now into, so in total, that's 3. This is our 4th one, if we include yesterday's. Angle side congruence, which says that if 2 angles and a non-included side of one triangle are congruent to 2 angles and another non-included side of another triangle, then there is enough information to say that the triangles are congruent. So you'll notice in the diagram here, this time the congruent side is not the side between the pair of congruent angles. But that's okay, because this is still enough of a statement to defend that they are in fact congruent. So in this particular diagram, zoom in here a little bit. If angle A is congruent to angle D, angle B is congruent to angle E, and side BC is congruent to side EF. Thanks to angle side congruence, there is enough information then to say that triangle ABC is congruent to triangle DEF. Now, you'll notice that the gloves are coming off a little bit on these next 4 examples. It's all on us. We're gonna have to make the statements and then defend with our reasoning. So, number 4 here, we've been given that YZ bisects angle WYX and that angle YWZ, which is right here, is congruent to angle YXZ, which is here. We're trying to prove that triangle WYZ is congruent to triangle XYZ. So as usual, we want to restate our given information because we're going to use that in our defense here later. So we'll say YZ bisects angle WYX, which is given. And then we're going to restate that angle YWZ is congruent to angle YXZ, which was also given. Now, again, it says this is a sample angle side proof. So hopefully we can find at least one more congruent pair of angles and then a congruent pair of sides. So what are we thinking? What are we seeing here?
Y and Z, since that bisects.
Yeah, okay. So I'm going with the visual here. YZ, which is this segment, bisects what?
Well, that's not even what I'm trying to say. I mean, basically, if it's cut in half, I don't know which one.
Okay, so you're in the right space, but I'm gonna reread the given statement. And I'm gonna highlight it up here on my screen, which apparently there's a delay on. Segment YZ bisects angle WYX. So it's this really big angle here at the top. And what does bisect mean? Cuts it in half, which means these two little angles up here must therefore be congruent. Sometimes, I know it sounds childish, but as you're reading the statement, taking your pencil and tracing those parts, YZ bisects angle WYX is going to help your eyes focus on where that relationship is occurring.
Fair order.
Yep. So trace it out. Trace it as you read it in that order, and it's going to help you focus in on where your information's at.
Supposed to say WZX on the bottom.
Yeah, if it had said WZX, then that would say that these two. So simply, again, I know it sounds silly and juvenile, but using your pencil and following them in that order is going to help your eyes adjust and focus in on where your information's at. So we can then state, so we still need to state that. We drew it, but we need to state it. Angle WYZ, which is the angle on the left-hand side, is congruent. Now I want to make sure I stay consistent here. So if I started at W, I'm going to start with X. So angle XYZ. And that was thanks to the definition of bisect. So good news, we have two sets of congruent angles. Now we just need a congruent set of sides, preferably not between those two angles. What do you see? Now think, in order to not be included, I don't want to talk about this side and this side because those are included. So either we're talking about this side of both triangles or these sides of both triangles. How would you defend that? Did it say that YZ bisects this? This one's always sly because it seems so obvious that it feels wrong. But isn't this side congruent to itself? Yeah. Again, that's an easy one to miss because, like I said, it feels like it's so simple that there's no way it could be right. But it is. Segment YZ is congruent to segment YZ. And what's the property that allows us to say that? The reflexive property. Now, taking a look at my diagram here, do I have enough for angle side congruence? Sure looks like it. So we can then say that triangle WYZ is congruent to triangle XYZ, which was just the statement up above that we were trying to prove anyways. And this is all now thanks to angle side congruence. Good. We're moving right along, doing well. This next one's going to throw a slight curveball at us just because it's going to make us recall some information we haven't yet in these proofs. But it's still I still think it's fun. I enjoy these. So we're given a lot of information. We're given that angle ABC is congruent to angle CED. So ABC is right here. CED is right there. AB and CE are parallel. So I'm going to sketch in my little arrow on the line just so I can visually see that those two lines are in fact parallel because we were told so. And then C is the midpoint of AD. So midpoint, I'm going to go ahead and make a very clear, distinct point there because that must be significant. And then you'll notice that I've got 6 lines now, but that's because we were given 3 different statements to begin with. So I'm going to take just a moment and write each of those given statements because that's going to kind of be where we start at. So angle ABC is congruent to angle CED, which was given. AB is parallel to CE, which was given. And C is the midpoint of AD, which was given. Now again, we know we're going for that angle side congruence. So we're going to need at least one more set of congruent angles and then a set of congruent sides. So what do you want to roll with first? I'm guessing one of those given, maybe more than one of those given statements is a clue to get started here.
ACB is going to. Yeah, ECD.
Now, look at those though. Again, I know we don't want to trust fully the diagram, but does that angle right there look like it would be congruent to that angle right there? So that may not be the angle we're looking at. Maybe let's start with the side first. Side might be a little bit easier. Take a look at statement 3. C is the midpoint of AD. Where's AD at? Right there at the bottom, runs all the way across. If C is the midpoint, what could we safely say? AC is congruent, technically we'd say to CD. This one's sneaky because of how the triangles are oriented. So the C in one triangle is not going to correspond with the C from the other triangle. So this one's just kind of tricky. But how can I say that? How do I know that those two sides are congruent? Well, let me ask you this. Where's C located? How do you know it's in the middle? Because it's the midpoint, right? So based off of the definition of midpoint, that must mean if it's in the middle, the sides on either side of it must be congruent. Again, you know this, you guys know this, but sometimes it seems, it just feels like, man, I already know this. How do I defend it? So we can say that AC is congruent to CD. And that is thanks to the definition of midpoint. Now, what that tells me is I already used the given information that C is the midpoint. I've used that, probably already exhausted all the help that that's going to give me. And the first statement, well, that was just very cut and dry. It just said, hey, these two are congruent. Not much more we can take from there. What we haven't used yet is these parallel segments. Now, this one is a little trickier to see because of where they're located. But if you imagine AB and CE as your parallel lines, and then try real hard to ignore these little segments here that are going upwards, and instead imagine AD as your transversal. Take a look at this angle compared to this angle. Visually, we know these are the ones that should be the same, right? So I'm going to first go with my instincts and then try to defend them. I know that this angle, based off of the diagram, which I don't want to trust completely yet, those should be congruent. Here's my parallel lines. Aha! They are corresponding, and corresponding angles in regards to parallel lines are always congruent. Good recall. So we can say that angle BAC is congruent to angle ECD because they are corresponding angles. Now, because I've kind of labeled as we went, do we have two congruent pairs of angles? Yep. And a congruent pair of signs that are not between those two angles? Yep. So I believe we have enough to say that these two triangles are in fact congruent thanks to angle, angle, side. So triangle ABC is congruent to triangle CED thanks to angle side congruence. Got it. Moving on to the next one. Given 2 bits of information here. Segment PR bisects angle QRS. I'm guessing I'm going to need to trace that one here in just a minute when I'm ready for it. And angle PSR, which is right here, is congruent to angle PQR, which is right there. So I'm going to start off by restating what's already been given. PR bisects angle QRS, which is given. Angle PSR is congruent to angle PQR, which is also given. So that second statement, there's not much more we can pull from it. But that first statement, like I mentioned earlier, it may help to visually trace that information as we read it. So I'm going to zoom in real quick, get my little laser pointer, and I'm going to read it again. PR, which is this segment right here, bisects angle QRS. So that has me focusing right here. And what does bisect mean again? Cut it in half. So these 2 little angles down here must be the other two congruent angles. So let me write it out so I'm not losing track of what we're saying. So making sure I stay consistent here, I'm going to say angle SRP is congruent to angle. So if I started with S for one, I'm going to start with Q for the other. QRP. And why can I defend that? Definition of bisect. Okay. So we have 2 sets of congruent angles. Now we just need a set of congruent sides that's not between those 2 angles. Aha. You saw it this time. PR is congruent to PR. And why is that? That reflexive property. So as I look at my diagram, I have 2 sets of congruent angles, 1 set of congruent sides that are not included between the 2 angles. I do believe now we have enough for angle side congruence. So we can make our last statement, which is what we're trying to prove. And that is that triangle PSR is congruent to triangle PQR thanks to angle side congruence. Keeping that momentum, jumping right into this next one. This is the last one before we switch to our last special case of hypotenuse leg. This one's telling me that LG is parallel to JM. So I'm going to come over here to my diagram. I'm going to sketch in those little arrowheads just so I can know that these are my parallel set of segments. And then it says H is the midpoint of LM. So H is a midpoint. I'm going to make it a very clear point, probably going to be significant here in just a moment. So I'm going to start off with my given statements, just restating them. LG is parallel to JM, which is given, and H is the midpoint of LM, which is also given. So where's your head go to first? Midpoint certainly makes a significant, impact here. So I'm going to come over here to the diagram and again, trace it out. H is the midpoint of LM. So if H is the midpoint, where is it located at on LM? In the middle, which means what can you tell me about LH and HM? Or MH, I should say. LH and MH. Congruent sides. Yep. Because a midpoint cuts a segment in half. A bisector cuts an angle in half. So we can say LH is congruent to MH. That is thanks to the definition of midpoint. Now, that was the only segment that H served as a midpoint on, so I'm probably done using this statement. That's pretty much all I can pull from it, which then leads me to go up to my first statement. Something to do with those parallel lines must be giving me enough information to go a little bit further. So parallel lines are over here. What if I imagine GJ as my transversal? So we could go that way. What are they? They are alternate, because if you're imagining LM as your transversal, this is alternate side of this transversal. Are they interior or exterior? They are interior. Exterior would mean they're outside those two parallel. These are between them. Yep. And you said that's because they're alternate interior?
Yes.
Okay. So angle L is congruent to angle M because they are alternate interior angles. Now, here's a little snafu we walked ourselves into. I would like to try to prove this with angle side congruence, which means I don't want to prove these are congruent because that would be angle side angle. It's okay though, even though those are vertical angles and we could say they're congruent. Can I then prove that these are congruent to get angle side?
Yeah.
For what reason?
It would be the same alternate interior.
They are also alternate interior, just with a different transversal. So G and J are also congruent. So angle G is congruent to angle J. Also alternate interior angles. And as I look at this, then I have, again, angles, two angles and a non-included side. So I have enough to say that triangle LGH is congruent to triangle MJH. Thanks to angle side congruence.
We also put it in the midpoint too.
We could have. There's actually a couple different ways we could have done it. And so long as you can defend your statement, I'm not going to be picky. The only time I might get a little bit picky is if I ask you to prove it with a specific type of congruence and you find it a different way. What I might do is make a little note, say, hey, you are right, but I was looking for this way. I'm probably not going to count off that much, if any. But yes, we could have proven it with angle side congruence another way. Or we could have also proven it with side angle congruence, just depending on how we use that vertical angle and which of those other two angle pairs we used. So 3 good ways of solving it or proving it. There's nothing to solve it. We're just defending a statement. So yeah, that one's kind of sly because there is that variability there. But the goal is to make sure you're confident in the statements that you write down and at least have a goal in mind. All right, last page. Last type of congruence involving triangles. Like I mentioned a couple times now, this one is rather unique because notice it's not just saying triangle congruence, it's saying right triangle congruence. So hypotenuse leg only happens with right triangles. And the reason for that is because the hypotenuse only exists in a right triangle. So you guys might, I forget which algebra class it would have been in, but the Pythagorean theorem, a squared plus b squared equals c squared, that's the leg squared plus the leg squared equals the hypotenuse squared. So hopefully you've heard that term before. If you haven't, we're going to take a look here and just tie it into our notes. So it says that if the hypotenuse and a leg of one, I'm gonna highlight it here as well. Oops, too big of a highlight. Of one right triangle is congruent to the hypotenuse and a leg of another right triangle, then the triangles are said to be congruent. Now, also, I'd like to draw your attention to the extra notes down here below. It does remind you that the hypotenuse is the side that is opposite that right angle, and that a leg, which it has 2 of, is a side that is adjacent to the right angle. So there's 2 legs, 1 hypotenuse. Now, in this particular diagram, using hypotenuse leg right triangle congruence, we can say that if the hypotenuse, in this case, oops, wrong tool again, if BC is congruent to EF and AB is congruent to DE, and I should say, we should also be able to say, and because they're right triangles, we have enough information that we could state that triangle ABC is congruent to triangle DEF. Now, I personally have a beef with this one. They name it this something special, but in reality, isn't this just sneaky way of doing angle side side, which I said doesn't happen? Think about that, angle side side. Why are we doing it? Because right triangles like to break the rules, unfortunately. Since that angle is a very special angle, a right angle, a 90-degree angle, this one allows us to do that otherwise forbidden congruence, which otherwise is not proof. Right triangles are unique, so that's why we have this means of doing so. They're really sly. All right. So using this 2 examples here, first one, statements are given to us. So we're just going to kind of work our way through it, defending it. And then the last one for today, we're going to see it all the way through. So here we're given LMP and MNP are right triangles. That is significant because that means, okay, hypotenuse leg is allowed. And it's also telling me that ML is congruent to MN. So ML and MN are congruent. So you'll notice that the first two statements are just our given statements restated. The third statement is MP is congruent to MP, which is just the reflexive property. And if I look at the diagram, because they are both right triangles, which was stated, and because we have the hypotenuse, which was the ML and the MN congruent to each other, and one of the legs congruent to each other, that's all you need. Right triangles with congruent hypotenuse and a congruent leg is enough to say that they are congruent based off of hypotenuse leg. Actually, I'm going to go more specific. Hypotenuse leg right triangle congruence. Because it wouldn't have been allowed if it was just any other type of triangle. So our last one for today tells me that triangle WVX and triangle YZX are right triangles, which allows me to come in here to my diagram and put my little right angle indicators. It also states that WV and YZ are congruent. So WV and YZ are congruent. And it also tells me that X is the midpoint of WY. So three given statements, which we're just going to rewrite here to start us off. Triangle WVX and triangle YZX are right. I'm going to abbreviate triangles, which is given. WV is congruent to YZ, which was given. And X is the midpoint of WY, which was given. Now, as I think about each of those statements, we've already kind of used the fact that they're right triangles. That let me put in my little right angle indicators. And there's not much more we can say about these two segments being congruent. They are just congruent. But have we used the information from X being a midpoint yet? If I zoom in here, X is the midpoint of WY, which means it is located where on this segment? Oh no, my screen. All right, sorry for that little snafu. Again, as I was saying, X is the midpoint of WY, which means X is located where on this segment? In the middle, which means that these must be congruent. So I come over here and I can then state that I'll say XW is congruent to XY. And that is thanks to our definition of midpoint. Now, if I look at the diagram, then we were given a set of congruent legs. We were told they were right triangles, And then we were able to prove that the hypotenuse of each triangle were congruent as well. Do I have enough for hypotenuse, leg, right triangle congruence? Sure do. So the proof statement is that triangle WVX is congruent to triangle YZX, thanks to hypotenuse, leg. I'm gonna just be lazy this time, congruence. We already have enough statements in there that defend that they are in fact right triangles. I just don't want you to forget that hypotenuse, leg only works for right triangles. Good. That was fun.